We already looked at attribution studies for monsoon trends where you make different simulations, one without greenhouse gases and aerosols, or separately without greenhouse gases and without aerosols, and then with them, and you compare the trends in the two whatever number of simulations to say how much contribution comes from greenhouse gas, let's say, to the monsoon trend, and how much comes from the aerosols and so on. So this seems rather easy attribution, but the details are not always that simple. So there are a couple of methods of doing climate and weather event attributions. Obviously it gets much more complicated when there are extreme events rather than these long-term trends, because extreme events happen, they are abrupt or they are rapid timescale processes like floods, flash droughts or heat waves and so on. And then to say whether they were increased in probability or intensity because of human influence is the key question. What is it good for? Why do we want to do it? Not always clear, especially when there is a rush to do immediate attribution as soon as a big event happens, like the big heat wave in the Northwest in July of 2021, or the massive cyclones or hurricanes, rapid intensifications, and so on and so forth. But one can imagine that if you did these studies for a number of cases and you identified, let's say in India, some part of the country is beginning to have more and more heat waves or more and more cyclone impacts, more and more extreme rainfall, and it turns out that they can be directly attributed to increasing greenhouse gases or increasing dust coming from the Arabian Peninsula and so on, then maybe there is a way to add resources to deal with the extremes in terms of mitigation and adaptation. Okay, but the science of attribution itself is obviously very important, and it's not done in one particular method right now. Different groups use different types of methods, and this couple of podcasts I will just focus on introducing the methods. So here is an example looking at monthly temperature equivalent in degrees centigrade. So we are looking at total temperatures and the return time in years in terms of the jumps in temperatures. So return time of extremely high monthly mean temperatures in the western Russia in the current climate, which is this red line here, and in earlier climate, so earlier climate, which means potentially when the human impact was low, and the dashed line shows monthly average temperatures. So here we are, and the dotted line shows the magnitude of the heat wave in 2010, which is a specific event. The gray arrow shows the departure from the average in the magnitude. So when the temperature change magnitude is considered, this is the change from the average to the particular heat wave that occurred in 2010. So you can see that in a prior climate, earlier climate, where presumably human influence was less, there was a possibility of a heat wave during that time, and it was amplified a slight bit by the human activity in the current climate, assuming that the current climate is all related to human activity. Of course, there is natural variability included, because it's possible that, for example, a certain phase of El Nino or Pacific Decadal Oscillation or the North Atlantic Oscillation would favor higher amplitude heat wave even in a natural variability. Okay, nonetheless, the other axis here shows how the return period was changed from the earlier climate to the current climate. So it has gone, the event return period changed from just over 100 years down to this is a nonlinear scale here, so you have to be careful. It came down to about let's say 60 or so years. So there is a significant reduction in the return period, which means the attribution framing matters. The question you ask was the probability of the event changed, or was the intensity of the event changed? So there were two separate studies published, and they seemed apparently contradictory, and then people jumped on it saying, haha, we don't know what we are doing. So skeptics of science can use these things, and media can also kind of report them separately, and then without realizing they may have the headlines differently. For example, this study would have said the heat wave was not made worse by global warming, whereas this one would have said the heat wave was made to occur because of the global warming. So it turned out scientifically the difference between the two studies is not really significant. It's just that the questions they asked were different. One asked whether the amplitude of the heat wave was significantly changed by global warming, and the answer is not much. And the other asked whether the frequency of the event was changed by global warming, in which case it is significant. So this is the issue with doing the attribution studies. So a schematic demonstrating 6 individual steps from identifying the meteorological drivers of an observed impact, what happened, to a robust attribution statement that can be communicated to stakeholders and the general public. Image in step 6 is from the Raising Risk Awareness project that's linked in here. So the first step is to see detect a signal. What happened? So you look at daily precipitation here, extreme wet event, analyzing observed data, use reanalysis products and reports on impacts to develop a narrative of the extreme event. And then you define the event, where it happened, what variables were involved, whether it's precipitation, heat wave, storm surge, and so on. How rare was the event? So that has to be done using the observed data and reanalysis in terms of the return period, for example. In step 3, the model evaluation. So for attribution, you have to go back to the model because you want to take out separately the effects that you are trying to attribute, the cause that you are looking for in terms of attribution. So does the model include key processes of creating these heavy rain events or heat waves, etc.? Does it reproduce the statistics of the return periods or the 95th percentile, 99th percentile of the extreme event, and so on? Okay. In step 4, you estimate likelihoods, so actual, counterfactual, 1 in a 100-year event, and so on. So you are now slowly introducing terminology here where calculating change in likelihood and using as many methods as possible means that you are getting into attribution methods. So when you say changed risk of a climate or a weather event, means you are comparing its occurrence either in terms of amplitude or frequency or return period in a counterfactual climate or weather where you are looking at a world where there was no human influence. So you have to somehow create model simulations of the counterfactual world. This is very important. And then you look at current simulations if the model captures the event properly, and then you compare the counterfactual world with the real world and say how global warming in going from a no human impact world to the human impact world changed the statistics of the event. So interpreting and synthesizing comes in terms of change in risk. What is the overarching result? Are some methods more robust than others, and so on? So this is the so-called risk approach, or the Oxford approach, where such counterfactual method is used to say how global warming has changed the risk of such an event, and then you can use that to say in the future how this risk will continue to change. There are places where risk may go down, there are places where risk may go up, and it depends on the event. It could be for heat wave, it could be for extreme rainfall, it could be for storm surge, for cyclone hits, and so on and so forth. And then the last step is communication. How to communicate the confidence in this attribution or the change in risk, and who is asking the question. For example, if a heat wave comes and you say the amplitude of the heat wave was increased by 2 degrees, then the farmer may think that's going to affect his crops, but a health worker might say that's not a significant change in terms of the impact of a heat wave on the community that the health worker is looking at. So vulnerability to the heat wave depends on a neighborhood scale, whether people have the infrastructure to take the public transportation, air conditioning, etc., versus neighborhoods where people are rich and they have air-conditioned cars, and so on and so forth. So who's asking the question matters as well. Okay, so attribution is obviously something that has to take care of all these issues of what question you ask and who asks the question and how you do the attribution. So we looked at one approach where risk approach is called, where you go and try to create counterfactual world. I will say a little bit more about what we mean by that and how they are created in the next podcast. And there are other approaches that we will look at in the next podcast. So this is a good way to start the setting of the attribution problem. So I just wanted to add these details because before we just said models did this and that to attribute trends in monsoon to aerosols, but this is a little bit more about what are the fundamental questions about the attribution science itself, and what are the different methodologies and how they depend on the questions you ask and how the extremes are defined. And they also answer slightly different questions, as we will see in the coming podcasts. Okay.